Hello everyone and welcome back to an L582 Modeling and Control of Electric Machines and Drives. During the last weeks we've been talking about the synchronous machines, especially in the generator mode. We talked about it at the very famous and widely used kind of machines in all the power stations connected to grid or even isolated. So you have the synchronous generator anywhere. And we have put some effort to make those concepts of this machine just more familiar with you, just trying to understand the construction of the machine, the theory of operation, how this generation happens inside the machine, the equivalent circuit modeling, so you can have a mean to predict the performance of such a machine when connected to an isolated load or even connected to the grid, and talked a little bit about how the machine can work while connected to a load, even if it is an isolated load, or when it's connected to the public grid and holds to the public grid's terminal voltage and frequency. And we talked about the parallel operation of the machine. So if you have more than one generator connected in parallel to feed an isolated load, or even talking about if you have multiple generators connected together as a parallel operation for the grid. Okay, and we ended this talking last time talking about the synchronous motor. So we talked about the synchronous machine when working at a motor mode, which is not very well, just not very famous application for the machine, but still can be used. Okay, and by this we ended our talking about a very important kind of machines that you will be encountering in your daily life at work most of the time if you're dealing with power system engineering especially. Okay, starting today, we'll be talking about the very famous and widely used machine that is basically you can use in any industrial facilities, not just power system facilities, and because that is the workhorse of industry. I don't have a specific number for now, but I know that more than maybe 90% of the all motors you'll encounter in any industrial facility will be of the type 3-phase induction motors. So we'll be taking time with it. Again, studying its construction, theory of operation to understand how it works and how it develops its torque as a motor, because we will be dealing with it as a motor most of the time. And we are also dealing with the modeling of it, how to predict its performance, and for this we'll be having more time talking about the speed control of it to understand what I mean by drives and the variable speed drives of the motors, and we'll be talking about the starting of the machine and understand how this happens. And we'll end a little bit by talking about the generation mode of this machine, because again it's most widely used as motor than a generator. Okay guys, so for here we will start talking about 3-phase induction motors. Okay, so I'm very specific here. We are talking about 3-phase machines. We will have a little bit talking about single-phase induction motors after we are done with 3-phase, but the most widely used one is the 3-phase machines. So we'll be talking basically about 3-phase induction machines, and not all machines, but specifically motors. Like I said, we'll be focusing on the motor mode of this machine because that is the widely known one. Okay, that's why we call it the workhorse of industry. Okay, you'll see that kind of motors almost everywhere, so that's very important to put time and effort to understand its operation and how to work with it. Okay guys, so I'll be starting like usual by talking about the construction. Okay, how this machine is built. Okay, so like any other rotating machine, we have two members, a stator, that's the stationary member, and a rotor. Okay, so it's become a habit now. We deal with this in DC machines and in synchronous machines. So we're now talking about it here. I'll start today talking about the stator of the induction motor. Okay, why? Because it's very easy now. The stator is the same as the stator of synchronous machine. Okay, so we're not taking you far away. It's the same stator of the synchronous machine that you may has slots holding three-phase winding. Okay, so we have three-phase winding and these slots of this kind of machine. If you remember when we looked at this before, when we're talking about synchronous machine, that's how the stator of the machine looks like. Okay, so the gray part, the bigger part here, the iron core of the stator, and it has internal slots that you place your winding. Those you've seen here as red, blue, and yellow. So the red, blue, and yellow, because they're three-phase winding. So the red is phase, say, phase A, and the yellow is phase B, say, and the blue is phase C. Okay, so like you've seen here, those gaps inside the iron itself, we call it slots, where you just put your winding, a three-phase balanced winding. Okay, guys, so that's what we're saying. That was the same stator used with synchronous machine, but we're using now with the three-phase induction motor the same stator. Okay. Okay, so it has slots holding three-phase winding. So not just any kind of three-phase winding, it's basically balanced three-phase winding. Okay, when I'm saying balanced three-phase winding, I'm gonna grab you the photo I think we dealt with before that. Yeah, okay, it is just some sort of a schematic to give you this idea. It's just we have three sets of winding. They are separately, they are not connected together, but the three-phase winding that can be connected after that to be any connection Y or delta. Okay, guys, so let's just call the red one here A, so that is A, so this will be A dash, and the blue one here, call this B, so this will be B dash, and the black one, say C, and this C dash. Okay, so those are balanced three-phase winding. What I mean by balanced three-phase winding, okay, that means they have exactly the same number of turns. So we're talking about coils, and every coil has turns, number of turns, so they have the same number of turns with the same wire size. Okay, so those are wires made of copper most of the time, so it has a size, a cross-sectional area, and a length. So that means you have a typical three sets of winding. Okay, but separated by 120 degrees in space, like you see in here. Okay, so if you have the axis of each one of those to look at, actually it's not the axis, but look at here. So from A to B, this is 120 degrees, and from B to C, this is 120 degrees, and from C to A, that is 120 degrees. Like this, you have what we call a balanced three-phase winding. That means they are typical winding and have 120 degrees phase shift. Okay, how you do this? It's just like we saw here in some more realistic stator like that. Okay, so in the other photo we just used one slot to represent this, so it was here too. It's a design parameter, so it doesn't matter, but for now, like you see in here, like you see, it is just three typical winding, but they are evenly separated like this around the circumference of the stator. That means they are just 120 degrees apart from each one. Okay, guys, that's what makes them balanced three-phase winding. Okay, and they have to be balanced actually to just achieve the required performance of this kind of a motor. Okay, let me try to be more realistic here, and I'll grab you this photo from Dr. Knight's online website. You can actually see it for yourself, but I need to have a closer look at it with you. Okay, okay, so that's what I mean by the just the realistic thing of the three-phase induction motor. You'll be seeing this a lot again, as I said. Okay, so that's why let's talk a little bit. So that is the lock of the motor in its case. So this bluish stuff, this we call it the motor case. So yeah, this is the case, the outer case of the motor itself. It holds all the parts inside it. Okay, this is here, you'll find some data. We call the motor name plate. Okay, that's where you can find all the manufacturer data about this motor. We'll be having a sample of this and illustrate every single item in it in later classes. But here you can find all the data you want about the motor, and it's very, very important to look at it when you're trying to do anything. Okay, so for us in the lab, we took this data and put it in a label on top of the working benches you have seen already in the lab. But when you're talking about a realistic motor out there in the field, you have to look at this nameplate to find the data of this motor. Okay, this guy is called the terminal box. From its name here, you find the terminals or the winding, and now you can make connection of it to the supply. Okay, this here is a cooling fan. Okay, it's attached to the shaft, so it rotates with the rotor. So whenever the motor is rotating, this fan rotates and just pushes air to cool down the motor, because you have a lot of heat, because you have losses, power losses, and this power losses inside the machine translates into heat. Okay, so we need this fan to try and just cool it a little bit. And if you see out there in the case, you'll find those slots here inside this guy. So those provides air guiding. Okay, so let's try to guide the air around the stator case again to make it better cooling for the motor. Okay, guys, to the same motor here on the right hand side, but it's taken apart. So again, that is your case. Okay, inside here, those guys we see, will take a better look here at the stator winding. Those are with stator three-phase winding. This black guy is the fan cover. So this fan, cooling fan, cannot be just lit like that, because it will be just not safe. Anyone can just be hit with it. So we place this cover over it. And if you've seen here, and this guy here is your rotor. Okay, so that is the rotor. We'll be talking about it maybe by the end of this class or next time. This is the shaft, the moving shaft of the machine, and that's where you connect to your mechanical load you want to drive, you want to rotate. What is a fan, a pump, an elevator, and any kind of thing you're trying to rotate with your motor. Okay, and this guy, we call it the bearing. Okay, the mechanical bearing, those what holds your rotor to rotate freely. Okay, so this case here is just plugged into this guy, so this thing plugged into the case. Okay, and just this rotates with the rotor and makes sure now this shaft is just holds its place while it's rotating. Okay, guys. Okay, the same thing here. So that is the stator, like you're seeing from inside. So you have this slots inside here. So those guys are the slots where you're placing your winding inside them, and now those are your winding. If you can't see them, they are just winding. Okay, those three-phase winding of the stator. Okay, you have copper coils, copper winding, and you also can see them here. If you see here, those just the wires going inside the slots, and the overhang or the connection is just coming from outside like this. So the winding goes inside the slots like this, and you just connect them, or you complete the turns outside here like that. Okay, guys. And of course, that's still the outer case or the outer frame, whatever you want to call it. Okay. Again, that is the rotor. We'll be talking about it after this. So, but take it for now, that's the rotor of the machine. Okay, guys. So that was a realistic look of the three-phase induction motor. To just look at it, because that's very important. Again, you'll be seeing this a lot. So it's better to have a look at it. Okay, so the stator of this machine, like we said here, have three-phase winding, balanced three-phase winding. That means there are typical three sets of winding separated by 120 degrees in space, like we have seen here. Okay, but what about the supply? So the stator balanced three-phase winding are supplied by an external balanced three-phase voltage source. Okay, because we're talking about a motor, so the input is mechanical power. It's coming from the source. Because we have three-phase winding, you need a three-phase source, and we need it to be balanced three-phase source also, like we have talking about the winding to be three-phase balanced winding. Okay, what do we mean by balanced three-phase voltage source? We talked about this before, but it's good to say it again here. So balanced three-phase voltage source, that means of the three phases, the three phases have the same voltage magnitude and separated by 120 degrees phase angle. Okay, so for example, if you're having the voltages like this, so the voltage applied to phase A will be V as a magnitude cosine omega et. So VB, the second phase like this, will be V having the same magnitude like A cosine omega et. Omega et requires mean they are having the same frequency, and that makes sense here. Minus 2 pi over 3, which is 120 degrees, but it's in radians here. VC equal the same magnitude V, sorry, cosine omega et minus 4 pi over 3, okay, or this can be plus 2 pi over 3. They are the same number actually. Okay, so that I mean by balanced three-phase voltages. Okay, and that's to keep in mind. A balanced three-phase winding fed from a balanced three-phase supply, voltage supply, produces a rotating magnetic field. That all we said before, but didn't explain why. That's the day when we're explaining how this happens, okay? But it will produce a rotating magnetic field. What I mean by rotating magnetic field, that is means its magnetic poles rotate around the stator in the synchronous speed. So those poles rotates by speeds, which is the synchronous speed, ns equals 120 f over p, where f is your frequency in hertz and p is the number of poles of this, the numbers of those poles we were talking about here. So that is the whole point. If you have a balanced three-phase winding and feed them from balanced three-phase supply, you are creating a rotating magnetic field. Okay, guys? How this happens, that is how we'll be now trying to discuss now in great details. Okay? So let's talk now about the rotating magnetic field. Okay? So again, to have a rotating magnetic field, you need balanced three-phase winding fed from a balanced three-phase supply. Okay? So that means you're trying to get this guy. A balanced winding means you have typical three-phase sets of winding like this and fed from a balanced supply. That means you have balanced three-phase voltages just like those guys. Okay, so if you have it like this, now everything should be just set. Okay guys, I'll be calling the windings, those windings, this here again, that is A dash, and I'll get the red waveform here, that is a voltage applied to phase A, that's going to phase A, and the blue one I'll call it phase B, so this will be and this B dash, and again this blue waveform goes to this, and the black here will be C dash, and here's the voltage waveform going to this winding. Like we've seen here, those are three-phase balanced winding because they're just separated 120 degrees and they are typical number of turns and size and everything. And this is a balanced voltage sources because they have the same magnitude like you're seeing here. They are the same magnitude. And you have 120 degrees phase shift between them. So now we have all the conditions we need to create a rotating magnetic field. How this happens, let's discuss this a bit. Okay? So let me say this. For each phase, so for each phase of them individually, okay? So if I just take one of them individually, one phase, so A, B, C, whatever you're taking, just one of them individually, okay? That means it is a coil or coils connected in series, whatever it is, okay? Fed from a sinusoidal voltage source. This creates, okay, what we call pulsating magnetic field. Okay, what I mean by pulsating magnetic field, just imagine that I have, that's an iron core like this, and I just have one coil like this. Okay, so consider this any phase of them, because any phase of them will be just like this. So call it phase A, for example. Okay, if you have a sinusoidal voltage source applied to it, so a current will move in through it, and this will now turn into an electromagnet, and now it's given magnetic field. Okay, but how this magnetic field happens? Just look at the current moving here. With time, it is sinusoidal or cosinusoidal, whatever it is. That means it changes in value and polarity. It's sometimes positive, sometimes it's negative, okay? So the magnetic field that will be created from it, magnetic field phi, will be taken almost the same shape. It's also positive, negative. That means sometimes you will have the North Pole here and the South Pole out there, and sometimes this will be a South Pole and this will be the North Pole, because sometimes it's positive, sometimes it's negative. And even this changes magnitude because the magnitude of the current keeps changing with the change in time, because that's sinusoidal current. Okay guys? That means that we call it a pulsating magnetic field. It pulsates because it changes value and it changes polarity. Sometimes the magnetic field is a North Pole, sometimes it's a South Pole, sometimes it's a maximum value, sometimes it's zero. Okay guys? That's why we call it pulsating magnetic field. It's far away from what we call a rotating magnetic field, where you find that the rotating magnetic field, guys, is fixed value and rotating. What I mean by rotating, changing position. Okay, so the rotating magnetic field mean those guys here are producing poles. Okay, those poles are just going around and around. Okay guys, so that means they're having somewhere here a North Pole, a South, a North, a South, a North, a South, something like that, and those guys have the same magnitude, does not change magnitude, but they change position. They are just rotating in a certain way but a certain speed. Okay, but that's confusing. For each phase of them, it doesn't look like that. For each phase of them, it's just pulsating. It's not going anywhere, so it's just holds some position. But sometimes it's north, sometimes it's south, and it changes value. That we call a pulsating magnetic field. It does not rotate and it changes value. But here comes the magic. Because we're not dealing with just one phase, we have three phases and they're just from three-phase supply. Magically, the combination of the three phases together will just bring you to this rotating magnetic field. So a single phase of them, just one winding, A, B, or C, one of them fit from a single phase supply will give you a pulsating magnetic field. That means if I take, for example, on the same thing here, let's talk about phase A, for example. So sometimes this guy will be a north, sometimes it will be a north, sometimes it will be a south, and this guy will be sometime a south and sometimes a north, okay? But it holds in its position and it just changes polarity and it changes magnitude, but it does not rotate around, it does not go anywhere like this. But if you have excitation by three-phase voltage to the three-phase winding at the same time, you will thus the resultant magnetic field of those three together will be just give you this action, that's you having a rotating magnetic field. How this happen? Let's try to understand this together. Okay, guys? So I'll be taking some positions here and some time instance for field, okay? So I am taking those two again, okay? Okay. Yeah. So I'm getting those three-phase voltages I'm trying to get here. So the three-phase voltages here, and I'm getting my winding distribution. Okay. Okay. And I'm going to here to just instant of them. So that is instant 1, and I'm looking at this, and I'll just choose this instant here. So this instant of time, and I will just try to have this time. So at this time here, let's look at the voltages here, okay? Again, so the red one is A, the blue one is B, and the black one is C, okay? So at this instant of time, because we're just dealing with time here, at this instant of time, the voltages will be just looking like this, okay? From here, you will find in this, the blue one, B, is crossing 0, so VB equals 0. And VA is positive. Sorry, it's negative. Yeah, the red one here is negative. And VC is positive. You can see in here, the black one here is positive, okay? So, how this applies to the winding? Go to the B, which is the blue winding, does not have voltage. That means no current passing through it, and that means zero flux. That does not produce any flux, okay? But for C, which is the black winding, it has positive current moving, okay? Positive current means it go through the positive current means it go through the X. So the positive means go in the X coming out of the dot, okay? It's just a notation we are using here, okay, guys? That is the positive. And the negative is just the opposite way around, okay? So for the positive here, that means the current go from here and comes out from there, okay? If you apply the right-hand rule, the magnetic field will be just perpendicular to this direction, and it will have this direction, okay? To the black one that's coming here from C, okay, guys? So that's the direction of the magnetic field of phase C. What about phase A, the red one? Phase A, it'll be negative. That means it will be just the current going through the dot coming out of the cross. Okay, guys? So I'll be using the right-hand rule. It will be just on the opposite direction. Again, if you just plot this, it will be perpendicular to it here, but it's going in this direction because it's negative. So that's the magnetic field coming from A, and that is the magnetic field coming from C, and B obviously doesn't have magnetic field at this instance because the voltage of it is 0. So the resultant of it, so that means the summation of them will be just graphically here in this position, guys, between them like this. So that is the total magnetic field at this instant. Okay, guys? Keep that in mind and let's play around. Let's just go and try to do the same with the next time instant, somewhere here. Okay, so I'm getting this again, and I'm getting this again. Good. At a second instance of time. I'm just saying here what this happens with the progress in time, okay? So that was the first instant of time we took. Let's take another instant of time. After this, I will be taking this here, again with the zero crossing. So I will be taking this here at point 2, okay? So this is my point 2 here, and I will be going here to look at the second time, okay? That is instant number 2, okay? From here again, phase number A now is 0, does not have voltage, okay? It's crossing 0, okay? For the blue one, VB will be negative here, and VC will be positive, the black one here. Okay, guys? So we're doing the same notation. The red one, A now is 0, does not have any flux. Let's look at the blue one, B. It's negative, that means the current going into the dot coming out of the cross. And that means with the right hand rule here, you will be having the flux of it perpendicular to it like this, but take this direction like this here. Okay, that is from B. Phase C, it's positive, the black one. Positive means the current go into the cross coming out of the dot, okay? So the direction of the flux will be just again perpendicular to it here like this, and taking this direction. That is C. I'm using here the right hand rule of flux. That means the orientation, if you just hold your right hand and you have the orientation of all the fingers except for the thumb, so the rotation of this whole fingers goes from the cross coming out of the dot, it taking the direction of the current going into the coil. So your thumb will give you the direction of the magnetic field coming out of the coil. Okay, you should be taking this before. Okay, so again, our resultant flux will be having this direction. It's between them graphically like this. So the resultant flux will be just a summation of them, and it will be taking this direction. Okay, that is the second instance of time we took. Cool. Let's try and take another 2 instances. Okay, so I'm gonna get this again coming here. And this one also. Now I'm going to a third instant of time, just progressing in time, guys. So this was instant number 2. So I'll be just going to here and place my instant number 3. Okay. So here will be your instant on time here. Time number 3. I'm progressing with time. Okay, so starting here, that was 1, and there, that was 2. I'm moving with time to instant number 3. And be looking about the voltages again. Okay, guys. For now, the black one, which is VC equals 0, does not have any flux. Okay. The blue one, VB will be positive, will be negative. Sorry. Okay. And the red one, VA, will be positive here. Okay. So I'll be doing the same thing. The A now is positive, that means the current going through here, the cross, and coming out of the dot, okay? And that from using the right hand rule for the direction of the flux will be perpendicular to this guy and going this direction, this from A. That's the magnetic flux. And from B, the blue one, it's negative. That means the current going into the dot coming out of the cross. And this will be having a perpendicular magnetic field to it, but it's going this way. So this is the coming from B. Okay, guys? So the summation of those guys together will give you the resultant flux taking this direction. Okay, guys? That is the third instant. Let's even progress and look at the fourth instant. Okay, I'm going here and place it down there. And it's also this guy. That's a fourth instance of time. So that was instant number 3. I'll go here and take instance number 4. Okay, guys? So here is my instant in time. That is instant number 4. Okay, guys? Again, we'll analyze the voltages. Okay, here the blue one, VB equals 0. Does not have any voltage. Okay? Number A here will be positive, and number C here will be negative. Going the same path. So number A is positive. Again, that means the current go into the cross coming out of the dot. Okay, so the magnetic field will be having this direction. That's coming from A. From C, which is the black one here, it's negative. That means the current go into the dot coming out of the cross. So the magnetic field of it will be perpendicular to it, but go in this direction. Using again the right hand rule. So if you take the resultant of those two fluxes, will give you a direction here. That is the resultant of them. Okay? And here that's a pause. I'm pausing here and let's log back from the starting one. Here, look at the green arrow, the resultant magnetic field of all of the 3 phases. Phase A, it's here. Okay, it's pointing out there. Go into the next instance, it's going here. The next instance, it's there. See what I'm saying, guys? Okay. So from instant A, it was just like this, in this position. Now it's in this position. Now it's going here. Seeing what I'm saying, guys? It's rotating. The resultant magnetic field was here, and now it's just being vertical like this, and now it's going to the other way like that. So like I'm saying here, it is just rotating. Okay, guys? Okay, think I'm missing something here. Yeah, it's 3. So that's from here. That's number 1, instant number 1. Look at the green arrow. Now it's up here. Now it's in the northeast side. Now it is in the southeast side. It's rotating, guys. Okay? That's what I'm saying. That if you have 3 phases fed from 3-phase supply, and if you just look at the combination of the magnetic fields coming from those all together and look at the total magnetic field, it will be just looking like it's the same magnitude of flux, but it's rotating around it. Look at what I'm saying here, guys. Okay? So this guy is just rotating around the circumference of the machine. So here the magic of this. From 3 different phases, if each one of them was fed from a different supply, and I look at them, each and every one of them will look like a pulsating magnetic field that pulls fixed in position and keep changing magnitude. That we call the pulsating magnetic field. And it's not useful anyway, okay? But if you combine them together, so if you put those three-phase winding at the same core and separate them by 120 degrees and make them balance the three-phase winding, and rather than having just different three-phase voltage supply, you have three-phase supply that is balanced. That means the same voltage magnitude and have 120 degrees phase difference between the voltages applied to the three-phase winding. The resultant magnetic field will be rotating. That means it will be just having the same magnitude but keep rotating around the circumference of the machine. Okay guys, that's what we mean by a rotating magnetic field. And it's very useful to have here. If you just refer back what I said in the synchronous motor, the last lecture, by having this three-phase, you now can create a torque. Okay guys? So, that's what we just said here. Balanced three-phase winding fed from balanced three-phase supply creates a rotating magnetic field. What I mean by rotating magnetic field, it is having fixed magnitude and changing position, rotating, okay, at the synchronous speed 120 f/p. So you can control this speed of rotation by changing both the frequency and or the number of poles, okay. So that's what we said here. We just having the winding and the resultant poles were just a north pole here, there, and a south pole here and there, okay. Those guys will be just rotating around the circumference of the machine at this speed. And here comes the magic, okay. From this, if you have three-phase winding fed from three-phase supply, you are now creating rotating magnetic poles from stationary three-phase stator winding, okay. So the three-phase winding, the winding itself does not rotate because it's just stator winding, guys, so it's just stationary. It does not rotate, it does not go anywhere. But by this arrangement, we have created poles from them. Those can rotate by the synchronous speed, okay. And that is the very, very important thing to consider. Okay guys, an important hint here, the direction of rotation is governed by the phase sequence. So switch any two phases to reverse the direction of rotation. What I'm saying here, that you use the phases here to just go. So if you have the winding of the machine from the terminal box looks like this, so you have three winding, each one of them has two terminals, and you connect them by any connection. Let me just connect them in a Y connection. That means three ends connect together to give you the neutral point, and now you have the other three ends. It's up to you guys, okay. So if you put here E and connect this to phase B of the supply and connect this to phase C of the supply, now you have a direction in a certain you have a rotation in a direction, in a certain direction, let's say in clockwise direction, okay. If you just switch any two of them, usually you switch B and C. So rather than connecting this guy's blue to B, now connect it to C, and this C connected to B over the supply, of course, you will be reversing the direction of rotation. So rather than to be clockwise, for example, it will be anti-clockwise, okay. So yeah, that's a basic information to have in mind. That's even the three-phase induction motors, so you can just deal with this even in the lab yourself. If you wanna just reverse the direction of rotation of the three-phase induction motor, you basically switch any two phases from those by the connection to the supply, and it will just reverse you the direction of rotation of your three-phase induction motor. Okay, guys? Okay. Sounds good. So that was our talking about the stator of this kind of machine and how you can actually create the rotating three-phase or rotating magnetic field out of those balanced three-phase winding fed from the balanced three-phase supply. Okay, I hope you understand this, guys. I don't want to jump to talk about the router of this machine now because I don't want to confuse you. I'll let you some time to just try to absorb this information and understand how this happened. It's very, very important, and even we used these information back in three-phase on the synchronous motor, and just we said how the torque production in the synchronous motor happens. But back there we didn't illustrate how actually this rotating magnetic field happens, and we did it today, and I hope you understand what's happening here. Thanks so much, guys, for joining me today, and we'll be continuing talking about the construction of three-phase induction motors next time.